All right, today we're jumping into a story that's part engineering puzzle, part detective mystery. We're going to crack the case of how a team of engineers hunted down a totally invisible and dangerous problem on a new tractor. So let's start right where every good mystery begins, with the problem itself.
It's a fair question, right? I mean, these huge, powerful machines throw off an incredible amount of heat. So keeping that heat away from sensitive parts, and more importantly, the person driving the thing, well, that's a huge engineering challenge called thermal management. And in this story, something went very, very wrong.
So here's the situation. During testing of a brand new tractor model, engineers discovered something alarming. The spots where the operator actually works, the pedals, the floor, the controls, they were getting dangerously hot. And this wasn't just, oh, it's a little uncomfortable. No, this was a serious safety hazard that had to be fixed before a single one of these tractors could ever roll off the line.
Now, to solve a case, every good detective needs evidence. For these engineers, their key piece of evidence was a metric called rise over ambient, or just ROA. The easiest way to think about it is as a discomfort score. It's just a simple percentage that tells you how much hotter one specific spot is compared to the air around it. The higher that ROA number, the worse your problem is. And this is where the red flags went up. The absolute safety limit for ROA was set at 38%, but engineers were seeing multiple spots in the operator's area, the brake pedals, the platform, clocking in way above that. The heat wasn't just an issue anymore. It was officially a hazard, something that could actually injure an operator. So how in the world do you solve a problem you can't even see? I mean, you can't just stare at a tractor and go, there's the heat. You need a special tool. The engineers needed their own high-tech magnifying glass, and it's called computational fluid dynamics, or CFD. Just think of it as a super powerful digital wind tunnel that lets you see the invisible flow of heat and air. The whole process is really brilliant. First, they build what's essentially a digital crime scene, a perfect one-to-one 3D model of the entire tractor. Then they run these complex simulations. They turn on a virtual engine, let it get hot, and watch how that invisible heat moves around, which generates thousands of data points. This lets them analyze every single nook and cranny to hunt for the source of the problem.
So, armed with their digital wind tunnel, the investigation officially began. The team started testing different solutions, one by one, to see if they could get those dangerous temperatures under control.
Okay, first, logical guess. They tried adding foam insulation near the exhaust to just block the heat. Makes sense, right? They ran the simulation, checked the numbers, and pretty much nothing. The ROA on that left brake pedal barely budged. It was their first big clue, and it told them this was not going to be an easy fix. A total dead end. But they didn't give up. For their next attempt, they tried a more advanced, ceramic-based insulation material on a part called a deflector. And, finally, some real progress. The ORA on the right side of the platform dropped way down, right to the edge of that safety limit. So they were getting warmer, so to speak, but the real source of the problem was still out there, hiding. Now convinced they were on the right track with these deflectors, the team decided to double down. They designed a completely new one, this time targeting that really stubborn left brake. And the result? It was a huge improvement. The ROA dropped from a crazy 54% all the way down to 40.5. But wait a second. Look closely. 40.5 is still over the 38% safety limit. After all that work, the hottest spot was still dangerously hot. I mean, think about this for a second. They've added foam, they've used special high-tech insulation, they've designed a whole new part, and that one stubborn spot is still a major problem. It was becoming pretty clear they were just treating the symptoms, not the actual disease. So the big question became, what tiny invisible detail did everyone miss? So while they were hunting for this mysterious heat leak, the engineers decided to try something a little different. They started wondering if the engine's main cooling fan might have something to do with it. So they ran a side experiment, testing a completely different fan design called a ring fan, just to see what would happen. And the simulation showed them something pretty remarkable. This new experimental ring fan was clearly more efficient. It used less energy to run than the standard fan. For a big machine like a tractor, that translates directly into better fuel economy, which is a huge win. But did it solve their overheating problem? And the answer to that was a hard no. This is a direct quote from the research paper, and it says it all. While the ring fan was more efficient, it did absolutely nothing to fix the heat on the brake pedal. It was a classic red herring. A super valuable discovery for later, for sure, but a total distraction from the case they were actually trying to solve. Okay, so frustrated but also really determined, the engineers went back to their digital crime scene. They knew they had to be missing something, so they decided to re-examine the entire 3D model, almost pixel by pixel, just looking for any possible source of hot air. And that is when they found it. Believe it or not, the culprit was a tiny, almost unnoticeable gap around an electrical socket that was hidden inside the console. That tiny little opening was acting like a perfect nozzle, funneling a focused jet of superheated air from the engine bay right onto the left brake pedal. This was it. This was the smoking gun they'd been searching for all along.
But there was an accomplice. The analysis also showed that the shroud, that's the housing around the fan, it wasn't really doing its job right. The original design was actually creating turbulence, which just let hot air swirl around instead of getting pulled away efficiently. So a new, slightly wider shroud was designed to focus the airflow, making the whole cooling system work better to pull that heat out and away from the operator.
So after finding the real culprit and its partner in crime, the engineers put the fixes in place. They sealed that tiny leak, and they installed the new, improved fan shroud. It was time to run one last simulation. This was the moment of truth. Had they finally cracked the case? The results were honestly staggering. The left brake, our main villain, it plummeted from over 43% all the way down to a nice, cool 19.5%. The right brake dropped from 40% to just 17%, and the hand throttle plunged from a scorching 54% to a perfectly safe 20%. Every single hotspot was gone. It was a total, complete success. Case closed, but the good news didn't stop there. Remember that inefficient shroud? Well, the new, smarter design, combined with sealing that one tiny leak, actually reduced the power needed to run the cooling fan by over 8.6%. That's a direct improvement in the tractor's fuel efficiency, all discovered while solving a safety problem. And it gets even better. Not only did the fan now use less power, but it was also working more effectively. The improved shroud actually increased the speed of the air flowing through the radiator by 1.5%. So the entire cooling system was just working better than before. The final design wasn't just safer, it was more powerful and more efficient too. So when you really boil it all down, this whole investigation had 3 huge wins. First, and most importantly, it solved a critical safety issue and made the tractor safer for the operator. Second, it actually made the tractor more energy efficient, which is fantastic. And third, it was just incredible proof of how powerful simulation can be for hunting down these problems that are literally invisible to the naked eye. And that kind of leaves us with one final thought. This entire massive engineering puzzle came down to one tiny hidden leak. It really makes you wonder, doesn't it? What other small, invisible forces, from the airflow in your office to the data flowing in your phone, are constantly shaping the safety and the design of the world all around us? Thanks for joining us for this explainer.